Anyway, so tonight we're going to hear planes, trains, and automobiles chasing the shadow of the solar eclipses. When I saw this title and the description, I was like, okay, this is going to be good. This is going to be good. I will also say our speaker tonight is a full-blooded physicist. So what I mean by that is bachelor's, master's, and PhD in physics. Most of the folks we chemists, no offense, Alan. But anyway, so Dr. Amir Caspi did his PhD at the University of California, Berkeley. And since then, he did a postdoc there, and then he went to the Laboratory for Atmospheric and Space Physics. Did I get that right? Okay. At the University of Colorado in Boulder. Then he moved to the Southwest Research Institute, which actually is in San Antonio, but has a branch or division in Boulder, which is where he is now. And he actually works with a number of people who have spoken here in the past. So anyway, so please join me in welcoming Dr. Amir Caspi.
Thank you very much. Hopefully the microphone's working. Awesome. Thank you very much, Andy and LPI, for inviting me to talk about one of my favorite things, which is the sun. I'm not a lunar and planetary guy, but I'm lunar and planetary adjacent. As Andy mentioned, 80% of my office is lunar and planetary folks. So I'm very familiar with the Institute here, and thank you all for coming. So I want to start out by saying that a lot of what you see here was made possible by Dan Seaton. He couldn't be here today, but he is my close colleague at Southwest Research, and you'll see a lot of him featured throughout this talk, but he really helped make a lot of this happen, and he is sort of Dr. Eclipse these days. So unfortunately, Andy stole my first question, which is, how many people saw the eclipse in April? So, thanks, Andy. But that's right. But there were, unfortunately, a lot of clouds throughout Texas. So hopefully you got lucky and you managed to see totality and not just the run up or run down from that. The question then is, how many of you a month later got to see the Northern Lights? One person, all right. They actually made it down to Texas and various other parts of the United States that you wouldn't even consider, like Georgia was able to see the Northern Lights, lots of southern United States. And in fact, just 2 weeks ago, we had another bout of Northern Lights that managed to make it all the way down south to various low latitudes. Both of those things are related, even though it doesn't seem like it. But the sun is obviously what you see during a total solar eclipse, but you also get to see what used to be part of the sun when you see the Northern Lights. And so we live essentially in the atmosphere of the sun. And a lot of people don't realize that, but we are connected to the sun, our star. So I'll talk about the sun and why do we want to study the sun? So a lot of people forget, it's easy to forget, the sun is a star, right? It is our star, but it is a star. It is a thing that exists everywhere else in the universe that we only think of as pinpoints of light. But our sun, which is also a star, is more than just a pinpoint of light. When most people think of stars, that's what they think of. When most people think of the sun, they think of, well, okay, it's not a featureless little pinprick of light, it's just a featureless blob of light instead. But if you look more closely at the sun, it's not actually featureless. Now, this is a picture of what we call the photosphere, the visible surface of the sun. And you can immediately see there are these black splotches, and it's not just schmutz on the lens, it's not dust, it is a sunspot. If you look closely with a telescope that can actually see detail, you can see so much happening there that you can't see from far away. Well, you can see it from far away if you have a big enough telescope, which is what this is. And so the black that you see there is what we normally think of as the sunspot, but you can see that there's so much more. There are striations, there are things we call plage, and there are granules, which are those things that are essentially, they look like boiling water. They look like boiling water or boiling plasma because that's actually what it is. It is plasma that's being heated inside the center of the sun and rising up the same way that bubbles in boiling water do and releasing its energy. Each one of those granules or convective cells is the size of Texas. Yeah. So just imagine, like, you know, Earth could fit in this picture right here easily. The reason that sunspots are dark, they look dark. They're not actually dark. If you manage to like take a sunspot and take it away from the sun and put it somewhere else, it would be very bright. But it's dark relative to the sun. And the reason that is because sunspots are associated with what we call active regions. They are where the magnetic field that the sun has is concentrated and bunched up and very complicated. And you can see that evidence of that in this very splotchy image here, where white is magnetic field that's coming out at you. Black is magnetic field that's coming in at you. And the way that this is measured is by taking that visible light and looking at very specific lines in the spectrum that come out of it and looking at how they are formed. And then you use fancy physics that I don't know, and you derive what the magnetic field must have been to generate that light that you see. And you can see, if I go back and forth, those are associated with regions where that magnetic field is intertwined and complicated and also very, very powerful. Magnetic field there is on the order of 2,000 times the magnetic field of Earth, which sounds like a lot, but in the scale of the universe, it's actually kind of small. If you look at the sun in other wavelengths, you actually start to see the amazing complexity of the sun. These are images that are coming from the Atmospheric Imaging Assembly, a telescope that's looking in ultraviolet light. It's on the Solar Dynamics Observatory, which is by now a fairly gray-haired spacecraft, so to speak. It launched in 2010. It's still up, still taking images every 12 seconds or so. And as you can see, these are not real colors, of course, because it's ultraviolet light, it's false color. But as you can see, it's cycling through at different wavelengths of light or different colors of light. It's looking at very specific, what we call spectral lines. So there's a bunch of iron in the solar corona, and it puts out different wavelengths of light based on how hot it gets. And so if you measure those wavelengths of light, you can see the different temperatures. And so up there, you can see the wavelengths and the temperatures. And you can see that as you get higher and higher in temperature, you see less and less stuff around the sun because only certain things are hot. And those certain things that are hot happen to be around the active regions where the magnetic field is strong. And so that tells you the magnetic field on the sun has to be very important in heating up the plasma in the corona. And I'll point out, if you keep an eye on how that temperature is scrolling, right, we see temperatures that are millions of degrees Kelvin, which is also millions of degrees Fahrenheit. That's compared to the surface of the sun, the visible photosphere, which is a few thousand degrees Kelvin, 6,000 degrees Kelvin, or 10,000 degrees Fahrenheit. That's a factor of 100 or 1,000 difference in temperature. How does the corona get so hot? The energy has to get up there somewhere, but how? That's one of the questions that we try to answer when we look at the solar corona, and one of the things we try to study when we look at eclipses. In fact, the fact that the corona is so hot was discovered during an eclipse. You can look at the sun in ultraviolet, not just in different wavelengths, but you can also look at it in time. You can see the evolution of the sun. So this is just one particular wavelength, and you can start to see that on a large scale, things don't change very fast. But on a small scale, if you look at just little individual things, you can see loops forming and going away. You can see little teeny jets and outbursts. And if you look long enough, you'll see solar flares and coronal mass ejections erupting. You can look at the sun in X-rays, not just ultraviolet. These are images from the X-ray telescope on the Hinode spacecraft, a Japanese spacecraft which has contributions from NASA. And the reason that I brought this up is, first of all, X-rays are really cool. I study X-rays most of the time, but also because you can see that over time, there's a difference in how much X-ray emission you get from the sun. There's also a difference in the ultraviolet emission, but the X-rays show it really well. You can see in 2008, there's just little teeny pinpricks of light here and there. And in 2014, huge active regions, huge loops, lots of emission. The difference between these is that the sun was in the minimum of its activity cycle around 2008 and close to the maximum of its activity cycle in 2014. And you can see that that activity changes the amount of emission because more activity means more active regions. Yeah. Please. So the question for those who may not be able to hear it is this looking at the same part of the sun? The answer is, in some sense, you can't really say that any picture is looking at the same part of the sun because the sun doesn't have any solid mass on it. It's always churning and renewing itself. One can say pretty clearly that there's no way to tell if you're looking at the same part of the sun. But because it's kind of like a ball of gas, right? But unlike Jupiter, for example, which has a storm that you can identify because it's been there for a long time, it's kind of like saying, are we looking at the same cloud that you saw 20 years ago? And it's probably got some of the same water molecules in it, but is it the same cloud? It's like the clouds of Theseus, to make a very, very deep cut. All right. One of the important things that happens on the sun is eruptions. That is a solar flare coupled to a coronal mass ejection. And of course, you can see that there's a lot of complexity here. There's stuff going out, there's stuff coming back in under the influence of gravity. Just to give you a sense of scale, that's the size of the Earth. And this is how far away the moon is, if you put that to scale. Solar eruptions are important because, first of all, they're really cool to look at. But secondly, they actually influence us here on Earth. Let's look at a different solar eruption. This is another solar flare that happened, another coronal mass ejection. And if you look at it on a small scale, and again, by small, I mean many, many, many times the size of the Earth, you can see there's, again, huge complexity. You can see a lot of emission. You can see things happening relatively quickly. These are timescales of minutes here. If you go out a little bit, watch what happens as this thing explodes. You can see a wave propagating, not just where that flare happened, but propagating around essentially the entire sun, right? This thing sends out a blast wave that affects essentially the whole sun. In fact, you can actually have what it's called sympathetic flares, where the shock wave hits another magnetic field somewhere else and causes another flare to happen. I mean, this is enormous, right? Solar flares, in fact, or solar eruptions, are the biggest explosions in the entire solar system. They release the equivalent of about 1 billion atom bombs of energy in the time scale of a few minutes. They release more energy than all of humanity has ever used in all of its existence in time scales of seconds. And then some. If you go further out, you can see that not only do you have this shock wave that goes around the sun, but you now have a bunch of material that gets spewed out into the interplanetary space, or what we call the heliosphere. That is billions of tons of protons, electrons, ionized atoms that got shot out of the sun and are now, spreading through interplanetary space, looking for trouble. Eventually, those things can come and hit Earth, right? This is, of course, not an actual picture. This is just a movie, simulation. But all of those particles are streaming through interplanetary space, and they can hit Earth. They can also hit other planets. They can hit spacecraft. They can hit astronauts that happen to be in those spacecraft. And this is especially worrisome if those astronauts happen to be traveling to the moon or to Mars. Those particles also, when they interact with Earth, they hit Earth's magnetic field, and those particles are carrying some of the magnetic field from the sun. And that magnetic field can interact with our magnetic field, and that can cause the northern lights. The northern lights are essentially the end product of a solar eruption. It started 93 million miles away, kilometers, miles, and has now been brought to you. This is a simulation showing kind of what happens when that coronal mass ejection hits, and it interfaces with the magnetic field of Earth. It starts to peel away some of that magnetic field. Those particles can then start to dig their way in and hit the atmosphere, where they interact with the upper atmosphere, the oxygen, the nitrogen, and they make all the colors of the northern lights. And of course, those dots are the satellites that happen to be in orbit around the Earth, which also see those particles and sometimes feel the effects of those particles. That's what we call space weather, right? This is the cause of this stuff. Storms that go through interplanetary space, they interact with human assets and technology. You may remember in the late 90s, an AT&T satellite went down due to a big solar storm. In 1989, there was a huge power outage in Quebec in upstate New York caused by a coronal mass ejection that hit, and it caused the Earth's magnetic field to do this, and that causes power stations to blow up, literally. In 1869, you might have heard of the Carrington event. This was a solar storm that was observed by Sir Richard Carrington, and it was so powerful, probably the most powerful storm on record so far. It actually caused telegraphs to catch fire because of that storm that hit Earth. Airplanes are affected by these things. They have to reroute around the poles. The GPS that they use can be affected. You may know that your cell phones and your GPS started not working all that well during the time periods where we had the northern lights because of all of that interference. So understanding the sun is the first step in understanding the universe that we live in, understanding how the sun affects us. And even if you're not an astronomer, even if you don't really care about astronomy, the sun is the daily influence on all of our lives, especially as we become a highly technological society. But if you do like astronomy, like I do, the sun is also a laboratory to look at processes that happen not just here in our solar system, but in other solar systems, other stellar systems, maybe around other planets that might be trying to form life. How do they form life when there's a star that's spewing stuff at them and trying to kill them all the time, but also at the same time is the source of their heat and other life-giving properties? And it's also, very interestingly, similar physics that happens around the universe's most powerful things, like black holes, neutron stars, active galactic nuclei. Studying the sun allows us to study those processes by proxy. Okay, so how do we observe the solar corona? Something funny? Oh, don't worry, I've got plenty of dad jokes here. One of the ways in which humans observe the solar corona is eclipses. The reason that you need an eclipse is because the solar corona is 1,000,000 times dimmer than the bright disk of the sun. And most people, unfortunately, do not have the dynamic range to be able to see things with the contrast ratio of 1,000,000. Also, it's very painful to look at the sun that way. So if you have a nice big moon that covers up the disk of the sun, now you can suddenly see the corona. And humans have been doing this as long as there have been humans. So this is, of course, what happens with a solar eclipse. Everyone here, a lot of people here see it, so you know our moon happens to be exactly the right size, coincidentally, that when it passes in front of the sun, a lot of times it is just a smidge bigger than the sun. And when it does that, it covers what the sun, the bright disk of the sun, you can see the solar corona. Of course, the shadow is small, and so you have to be in the right place. If you are in the right place, you can see that shadow crossing over you. And those of you who saw it, of course, know what kind of transcendental experience that can be. And those of you who didn't get to see it, hopefully you will, because it is almost indescribable what it feels like. The sky gets as dark as twilight, not night, not deep midnight or anything, but it's twilight. You can see stars, you can see planets, you can see the solar corona. You can see, if you have a camera that can expose for a long time, you can see the solar corona out very, very far away from the sun. Technically, we're swimming in the solar corona. Well, standing. If you look at the solar corona more closely and you process the images, you can see all of that structure in the solar corona. And we'll see more of this, of course. Humans have been looking at eclipses, like I said, since there were humans. What you see there is a petroglyph, a rock carving in Chaco Canyon, New Mexico, that very, very likely represents an eclipse that happened around 1100 in the current era. And only 700 years later, we have a photograph of the eclipse. And of course, we've been observing eclipses ever since. Edison famously went to observe an eclipse in Colorado in 1878, and like most of us, failed to make his reservations in time and therefore had to observe from a chicken coop. Make your reservations early, folks. And you know, he was a scientist. He wanted to try and measure the heat from the sun. He had this experiment called the tosimeter. Unfortunately, like so many science experiments before it, it didn't work. But that's science. Sometimes things don't work and you got to try. No eclipse talk would be complete without talking about Dr. Jay Pasachoff. Unfortunately, he died a couple of years ago, but he probably holds the record for the human who has seen the most solar eclipses in one's lifetime. Jay worked at Williams College and was responsible for bringing a lot of people into the study of the sun and solar eclipses in science, including Dan, who couldn't be here. Jay's mentor, Jay's PhD advisor, was Don Menzel. Don Menzel basically started coronography, the study of the solar corona, in the United States. He opened the first coronagraph in Colorado and was Jay's PhD advisor. He also liked to make drawings of things at every eclipse that he would then give to people. So Don and Jay would go to a lot of eclipses, and then that same tradition was passed on to Dan and Jay. You can see Dan there in the yellow Williams shirt and Jay in orange shorts that he would wear at every eclipse. And so now Dan wears, thankfully, different orange shorts, but is carrying on that tradition. So one of the problems with observing solar eclipses, which many of you I'm sure experienced, is clouds. If you try to observe from the ground, unfortunately, sometimes there's water vapor in the air and it condenses and then it goes right in front of the sun and you can't see it. So people have been fighting this for over 100 years now. The first airborne observation of the sun during a total solar eclipse was in 1923 with some Navy biplanes. As soon as the plane was invented, people decided to start using it for solar eclipses. In 1925, the Navy decided to fly a Zeppelin. This is from the same family as the Hindenburg, but thankfully did not suffer the same fate. Charles Littell and company, Captain Charles Littell, put together a bunch of folks to observe the solar eclipse from that Zeppelin over Albany, over Montauk in New York. This happened to be in January, which is why they're wearing coats like this. They actually wanted to put the observatory on top of the Zeppelin, and they said, well, January in New York is not so good for that kind of thing. So they ultimately went inside into the cabin. And one of the best quotes from this paper that was written is that they assembled in the cook's galley and ate ice cold bananas. This is something you can find, by the way, at the National Air and Space Museum. It's a fairly amazing story. You can see the Zeppelin here. I'm gonna click through a little bit here if I can to jump through, but you can see the Zeppelin taking off. It's huge. and housed these folks, and they made observations of the solar corona. They had a number of different experiments, including a spectrograph that tried to measure the colors of light coming off of the sun. And you can see them huddled in there. And here you can see their observations of the corona. Now you do see, of course, the sun bouncing around all over the place. And it turns out that, you have something in the air, it's not all that stable. This is a problem that plagues us even to this day. Another famous airborne experiment for solar eclipses happened in 1973. The Concorde. It didn't just fly by itself, but scientists proposed and convinced the makers of the Concorde to loan them the prototype Concorde, #1, and cut a hole in the fuselage and so that they could see the solar eclipse. And why the Concorde? Because the shadow moves so quickly, you have to be supersonic to be able to chase it. And that's what they wanted to do. They wanted to chase the shadow of the eclipse so that they could see totality for more than just a few minutes on the ground. This is on YouTube. If you want, I turned off the audio. It is also in French, so you need to be very bilingual to get this. But our colleagues from the 70s were very inventive, and they put together these experiments and they put them on the Concorde and they flew it. You'll see very soon the lovely CGI of the plane in the eclipse track. They had to hit their mark within about 1 second to make sure that they could track the eclipse the way that they wanted to. The unfortunate part is when you fly supersonically, there's a big shockwave around the airplane. And a big shockwave means a lot of turbulence. And turbulence, for those of you who know about telescopes, is exactly what you don't want in front of your telescope when you're looking at things. Because if you've ever looked at the heat rising off the roads in Texas on a sunny day, you know that it makes things look very, very wavy. And so that makes life difficult for science. And even to this day, people fly airplanes. This is an expedition that happened in Antarctica, or near Antarctica, actually off the Falkland Islands, because sometimes eclipses happen over the ocean. In fact, about 73% of the time they happen over the ocean. And if you want to see it, you got to be mobile. So I'll tell you about an experiment that started right here, a few miles up the road at Ellington Field, where NASA has 3 WB-57 aircraft. Those aircraft are the only 3 WB-57s operating in the world today. They've been upgraded and I will say lovingly Frankensteined with lots of other parts to keep them up and running. And very importantly for the eclipse, they have been outfitted with a special nose cone that does that. That nose cone is basically a ball turret with a telescope inside. And it can look and track objects in the entire forward hemisphere of the airplane. And so as the airplane is flying, it can track objects or the eclipse, even if the eclipse is over there, without having to cut a hole in the airplane, which most airplane manufacturers do not recommend. This was actually developed, this particular system was originally developed for the Space Shuttle return to flight because they wanted, NASA wanted a system that could basically track the shuttle as it was lifting off so that they could get an advance warning if anything was falling off. And this is the 3rd incarnation of that particular instrument. Inside, this is from 2017, inside there's an instrument called Dynamite. That instrument has 2 cameras on board. One camera that you can see on your right is a visible light camera. It just observes in regular light, the kind we see with our eyes. And the camera on the left that has the mirror finish on the lens is an infrared camera. And that camera observes in what we call mid-wave infrared, or you might know it as thermal infrared radiation. So we call it thermal infrared because when you look at things that are approximately a few hundred degrees Kelvin, like people, then they glow in that particular color of infrared. The sun, it turns out, glows in that color of infrared for different reasons that we are trying to explore. This is a test image that was taken right before the eclipse. It was August in Houston, so you can see the tarmac behind me is about the same temperature as the surface of the sun. And this is the only picture in which I can say I look cool. So the aircraft is operated by two people, and I was not one of those two people. There's the pilot, and there's the sensor equipment operator in the back. And apparently you need training to do this. So they wouldn't let me in it. Liability. So we have here our intrepid flight crew, and they are amazing folks. You can see here this is a time lapse, obviously, from the cockpit, what happened during the eclipse. And you can see the shadow overtaking the airplane here. And then you'll be able to see, this is Don Darrow, who works up at Ellington Field and is one of the sensor equipment operators there, observing the eclipse from the best seat on the planet, or above the planet, as the case may be. Just like with the Concorde, they had to hit their marks within a time window of about 5 seconds. These pilots are amazing. They did it without practice. We just gave them the coordinates and they got there. And you can see here this lovely metaphysical image of Don looking at the eclipse on his screen while the eclipse is right up there above him. For those of you who are airplane aficionados, the airplanes took off from right here in Ellington Field in August of 2017. They went up north because that's where the eclipse was. On the way there, because we looked at stars, we looked at Venus, we used that to calibrate our instruments, basically. And then they went and you can see those little loopies over there in the northwest, and that was their timing control. They got there ahead of time, and then they went in circles so that they could make sure that when the time was right, they went right down the path. And why did they need to control the time so much? It was because there were two of them, and we were flying them in formation. We were flying them in formation 100 kilometers apart, about 60 miles apart, because we wanted the shadow to cross over one and then the other in series, so that instead of getting on the ground, it was about 2.5 minutes of totality. Up in the air, it was 4 minutes per airplane because they were traveling with the eclipse. And together, flying in formation like this, they could get about 8 minutes of totality. And again, they hit that perfectly. Now, it's a stabilized platform. The AIRS platform there has a gimbal system, but you can see that there's still some residual jitter. It's not that fast. This has been sped up. But there's a bunch of residual jitter, and so we had to do some corrections for that. Thankfully, modern day computers are really, really good, and modern day programmers are very good. Dan, my colleague, was able to basically, that thing on the right, by the way, is a movie, is playing at the exact same time as the movie on the left. And you can see exactly how stable we can make it, basically to the pixel stable. And so that allows you to then put together all of those images and stack them up as much as you want to take an exposure as long as you want and do some fancy processing on it so that you can bring out all of the details and loops and things in the corona. Now, it turns out this is invisible light. It turns out that the visible light camera that was there is not a scientific camera. It was not optimized for observing the eclipse. And so while amazing, this is something that is not groundbreaking. But the infrared camera, it turns out, is something that people haven't really looked at before, because infrared emission, especially in that particular wavelength, is absorbed and it's emitted by the atmosphere. If you want to observe in that color of light, you have to get above the atmosphere. And that's one of the reasons we flew on the WB-57s, because they flew at altitudes of 50,000 feet, higher than most commercial jetliners, and above 90% of the atmosphere, above 99.9% of the water vapor in the atmosphere. And so they could see this. The false color, of course, where blue is dim, red is bright. And this is the image that we got after a bunch of data processing of midwave infrared for the corona. This is, to our knowledge, the first time that the corona had been good a resolution at this wavelength, and only maybe the second or third time it had been seen at all, given that you have to be in an airplane to do it. One of the interesting things that we saw is that thing on the left here is an active region. It's the corona that's above that magnetically active region, and it's millions of degrees. On the right is a prominence. You probably saw, if you saw the last eclipse, those red dots, right, that you could barely make out with your eyes. Those are material from the surface that has sort of bubbled up in the magnetic field, been caught in the magnetic field and gone up into the corona, which I liken to, pardon the analogy, a hernia. But it's sort of caught up in that magnetic field, and it is not millions of degrees. It's only about 10,000 or 20,000 degrees. And yet it is almost as bright as those millions of degrees in these colors of infrared. Why is that? It has to be different physics that's causing that emission, different contributions to that emission, and we wanted to find out why. So we repeated this experiment with a new instrument called SAMI. This was built by other folks at NASA Langley, and you can see instead of just 2 or 3, but this is where most of the action happens. And it's a system that feeds 4 cameras, and those cameras are specifically scientific cameras, and they observe in all of the colors of light from visible light down to the midwave infrared. And so now we were able to take observations, not just in one very big wavelength, but in 9 separate bands of light, from visible light to the midwave infrared. And I show this because, again, we have our intrepid crew here, and this is a different crew than last time. And also just because watching this thing take off is amazing. Those wings are 22 feet wide on an airplane that seats only 2 people. It's basically a glider with jet engines on it. And it is basically this majestic thing to take off. So this is the selfie. They took a picture from one airplane from the other airplane. You can see that airplane right there taking this picture. And that's the flight crew and the operators and the camera. They took off also from Ellington Field. They flew down to the coast of Mexico. And the reason they flew down there is just because that was where the angles were favorable to make those observations. And where we observed the eclipse was right over the coast over Mazatlan, basically where the eclipse first made landfall. And I'm now going to show you snapshots from them. This is from the visible light camera. This is in real color. So that magenta, the eel, that's what those prominences look like, because that is a particular hydrogen emission that you see that's there. Now, this has not been fully processed. There's a lot of structure out here that you can't see very well. We still are working on processing the data. There are 8 terabytes of data from this one mission. This is in the near infrared. So this is light we can't see, but close to the light we can. The shortwave infrared, all of this stuff is camera noise here. Again, we're working on processing that out. To our knowledge, this may be the first image in shortwave infrared that has been taken of the solar corona. And then 1 wavelength of the midwave infrared. Now, this doesn't look quite as nice as the others, but I'm going to show you what this image looked like before all the processing. So there's a lot of magic that was worked to try and pull the data out of the noise in that image. There's a lot more work to be done, but you can see you can see all of these structures glow differently in the different colors of light, and we're now trying to use that information to better understand why that's happening. We ran another experiment, which also has connections to Texas here. If you want to observe the eclipse and you are standing in one place, you get to observe the eclipse for a few minutes. What happens if you want to observe the eclipse as it crosses the entire United States? Either you have a supersonic aircraft, which we did not, or you distribute a bucket brigade of telescopes around the nation, and you have the eclipse pass over every one of them in series. So instead of chasing the eclipse, you make the eclipse chase you. In 2017, one of our colleagues, Matt Penn, who was then at the National Solar Observatory, formulated this experiment called Citizen Kate that distributed 60 teams, more than 60 teams with 300 volunteers, not scientists, students from middle school, high school, university, teachers, educators, librarians, people who hadn't necessarily ever observed things before with a telescope or hadn't ever seen an eclipse, gave them equipment and training and distributed them around the eclipse sites so that they could take observations and make basically a continuous observation of totality as it crossed over the United States. And this is one of the movies that they generated of the eclipse passing forward over the entire United States. You can see, of course, because not everyone's camera was aligned, a lot of wiggling here, but you can see things happening on the timescale of just an hour as the eclipse passed. In 2017, they had more than 90% coverage, thankfully. This is 2017. But in 2024, we decided to experiment with new teams and new science. And we deployed 35 teams across the nation with new telescopes. And those new telescopes measure polarized light. If you're not familiar with polarization, you are familiar with polarization because you wear polarizing filters on your face a lot, assuming you have polarized sunglasses. Those are important because they block light that waves in a particular direction. Light's a wave, right? And it waves like waves on a string. And if those waves are going in a particular direction, you either get them through your sunglasses or you don't. And that's important because if you are a fisherman or if you're driving and the road is wet, you want to cut that glare because glare happens to be polarized because it's a reflection. Reflections polarize light. It turns out that the light from the corona is also polarized because the light during a solar eclipse is not coming from the corona. It's coming from the surface of the sun, going out into the corona, bouncing around there, and then going into your eyeballs. And so that it gets polarized. If you measure the polarization of that light, you can learn things about the corona. Remember I said the corona is a million times dimmer than the surface? It turns out that as you go further and further away, the corona gets dimmer and dimmer by a factor of 1,000 or more. And so you can't do imaging of the corona with a single image. You have to start stacking things. And so we take high dynamic range by taking short exposures up to long exposures, putting them together, make a high dynamic range thing. Your iPhone does this automatically, but not to that level. Since I'm rambling on a lot, I'm going to go show you our first attempt at this, where we went to Australia because this experiment is complicated and we wanted to make sure that we knew what we were doing. And so we took some of our community leaders and went to Australia in 2023 and said, hey, here you go, here's a telescope, let's look at the eclipse. And we used that as practice so that we could see what we would see and understand what we would see in 2024. And here you can see this is a GIF that's going back and forth between two angles of polarization. So it's looking at light that is waving this way and light that's waving this way. And you can see that the corona looks different because the light is polarized. And so if you're looking at light that's polarized in a particular direction, you see different parts of the corona. It's much more evident, of course, if you color it. And so blue is now one of those colors, gold is the other color, and you can see that different parts of the characteristic polarization and the prominences, they look white, not because they're super bright, but because they're not polarized. They're not polarized because they are actually emitting their own light. And the way that they emit that light is not polarized. It's not a reflection. You can also actually color it based on the angle of the polarization. And then you get this amazing rainbow image where every color represents a different angle of polarization, and the saturation of the color is how polarized it is. If you're interested, there's a paper about this. I won't make you take the QR code. You can find me later for it. Okay, so deploying 35 teams means we had to become a distribution warehouse. We had to buy 35 telescopes, actually more, we had some spares, telescopes. We had to buy 35 tripods and cases for those tripods to go in, and shipping cases. And 35 computers. And we had to put all of this stuff together, and we were really good at Tetris. And so we got everything to fit basically inside one big case with some accessories in another case. And then we put all of those things together and we shipped them out to our teams. Some of them we shipped by car, and we went and did a training here in Texas, in San Antonio, where we did a hands-on training with folks. These are our community leaders who helped us recruit our 35 teams and train all those 35 teams. As you can imagine, it's not feasible for just a handful of people to train 35 teams on how to make these observations. And so we We did this hierarchically, and we trained people who then went to train other people. And most of these folks are educators at universities, colleges, schools, and they went and they educated all of their teams. And they held a lot of practices before the eclipse. They took the equipment and they went outside and pretended it was the eclipse and figured out how to operate the telescope. These are students, people who had never worked with telescopes before. And I'll start with the numbers here. We had applications, right? Because this was for people who weren't scientists. We didn't just choose people. We had people ask, and then we figured out who would be best able and suited to participate, trying to focus on underrepresented communities as best we could. We had 379 applications for 35 teams. We had to pick less than 10% of people, which was heartbreaking. We had more than 225 participants. 50% of those leaders were women. 75% of our regional coordinators that you saw in that other photograph were women. We had a lot of teams with Latino participants, especially here in Texas. We had 2 indigenous teams with indigenous participants. We had 10 lead trainers who were students. More than 50% of our teams had student participation, and we also had one team from the U.S. Air Force Academy that decided they wanted to come and observe with us. 100% of the teams went out on eclipse day to observe. Nobody had broken equipment. Nobody got sick. Nobody said, I'm not doing this. Everybody went out. Everybody set up. Everybody tried. And the only reason that some people didn't observe was because of the clouds. It turns out that we got quite a lot of success. We had people in Maine. We had people, actually, this is New Hampshire. We had people in Texas, clouds, unfortunately. We had people in Arkansas, more Texas. Everybody went out, everybody set up for the big day. Doesn't matter the weather. We had teams all over the country. And some people saw this, unfortunately, but they tried. They still took pictures, and some people were able to see the eclipse. And you can see here people using the laptops and the custom software. And some people got antsy and decided to analyze the data on their own, and they made these rainbow images. And some people got to see some very interesting solar structures. For those of you who are having trouble wrapping your head around this, this is an airplane, and this is a paraglider who we caught in full polarized light, paragliding in front of the eclipse. We had 36 community participation teams, including the Air Force Academy. 85% of them managed to get some observation of the total solar eclipse, despite the clouds. We had some professional stations. We had 47,000 images that got taken, over a terabyte of data, in calibration data that they took before and after, 2 terabytes of data, and you can imagine that we're still working through it. All data was uploaded, and we also had a bunch of news stories. And we didn't let people do this alone. Dan and I also went out, and just to prove that this could be done by anybody, our kids operated the station that we were at the Cotton Bowl. For those of you who may have been there, you may have seen us on the field. And this is the image that was taken from Dallas. We had a little bit of high haze, but you can see quite a lot. This is from the middle of, oops, I just turned something off. This is, you can see that this is the big prominence that a lot of people saw on the bottom. And then we also have other sites. This is only a handful of sites that you'll see here, but we have a lot of rainbow images processed from various sites around the country. We're working to figure out, how did the corona change over time during this 1 hour of the eclipse? If you want to read a really nice Washington Post article that was written about this particular experiment, it's right here. Again, I'll put this up later for those of you who are not super quick with your phones. All right, wrapping up, since I see Andy giving me the look. How do you want to observe the next eclipse? The next one, solar eclipse, is over Greenland, if you know anybody living in the far reaches of Greenland, Iceland, right over Reykjavik, and northeastern Spain. And that's going to be about a little under 2 minutes here, about a minute and a half or so here in Spain. If you can't make it to that eclipse, there's a much, much longer one, almost the limit of how long an eclipse can get. In 2027, it goes over the Strait of Gibraltar, goes over Tangiers, and it goes over here is the Valley of the Kings in Luxor, Egypt. Just imagine that scene. Just imagine. Of course, it also is in August in Egypt, and so it will be very, very hot. But if you can make it, 6.5 minutes of totality, right? Near the limit of how long an eclipse can get. Watch your email. If you want to go down under, go to Australia in 2028. There's another continent crossing eclipse this is, a few thousand miles of terrain. Now, granted, most of it's the outback, but it goes right over Sydney. Book now. If you like Australia, they also will have an eclipse in 2030, in 2035, and in 2038. So get your frequent flyer miles. And if you take your vitamins and do your exercises, the next one over the United States is in 2045. Be optimistic. Come on, come on. You can. If you can't wait that long and you want to see the sun, we have dozens of spacecraft in orbit around the Earth. We have dozens of telescopes on the ground looking at the sun. You can see in ultraviolet the solar disk. You can see coronagraphs. You can see things together. NASA, NOAA, ESA, the European Space Agency, they all put out images of the sun, not just for science, but also to understand space weather. NOAA, the same people who do our weather reports, also have a space weather office in Boulder. They look at these things all day, every day, to try and understand what's happening. This is an image from the ultraviolet imager on GOES, which is the same satellite that looks at our clouds and our rain, and is also looking at the sun in ultraviolet. Look at that stuff. I mean, that's amazing. And they just launched a new coronagraph, the world's first operational coronagraph, to observe the sun, to look at coronal mass ejections coming at us. I will be remiss if I forget to mention, of course, that we have 2 spacecraft currently orbiting very, very close to the sun. Solar Orbiter, which was launched by the European Space Agency and has some NASA instruments on it, is currently going around the sun well within the orbit of Venus. And it has an imager on board that looks in ultraviolet and it gets close to the sun, so it has really high resolution. And so you can see things that you just would have very difficult time trying to see from Earth. And then we have NASA's Parker Solar Probe, which is, as you may have heard it advertised, a mission to touch the sun, because it is flying inside the orbit of Mercury at a distance of only 9 solar radii. I can't do the math in my head, but it's really close. And here is something that it recorded as it flew through a coronal mass ejection during one of its passages near the sun just a couple of years ago. Just imagine flying through the atmosphere of a star. And that's what this spacecraft is doing. Can't wait for the eclipse. Go online and look at what your taxpayer dollars are funding, because it's purely amazing. So thank you very much for listening to me ramble. I hope you enjoyed it, and enjoy the sun. No, this is actually the website where we talked about our 2 experiments, the WB57s and Citizen Kate. And right now is not fully updated, but if you keep visiting over the coming months. We'll be putting up new images, new data, new scientific results from both of those instruments. The Washington Post one I can put up also.
I did the math for you, Amir. It's about 400,000 miles.
Okay.
Well, if you got a question, we'll take some questions, but wait for me to get there so we can get it in the mic here because we are recording. So watch what you say.
This is the one for the Washington Post article.
You mentioned we're presently at one of the peak, and a few years ago was the minimum. How much difference is there in radiation from there? And how much effect is that having on our current environmental problems?
So that is a very good question. The difference in the total amount of radiation, when you look not just at X-rays or ultraviolet, when you look at all of the light that the sun is putting out, the difference is less than 1%. It is something like 0.1%. This is something actually that my colleagues at the Laboratory for Atmospheric and Space Physics in Colorado have been studying for decades. And the difference between solar minimum and solar maximum is a small fraction of 1%. In total radiation. Now, if you look at X-rays, right, that's a factor of 10, factor of 100 difference between solar minimum and solar maximum. But most of the energy is not carried in the X-rays. Most of the energy is going to be carried in the other wavelengths of light. So in terms of asking how much does that affect our particular climate situation, even though the sun is 99 point something% of the energy that hits Earth, it's incredibly stable from that perspective. And the solar cycle, in terms of its activity, is only 11 years long. And we've been seeing, of course, effects on climate scales that span hundreds of years. So while the sun certainly has an influence, it is not necessarily the reason that we are seeing big swings right now. I'll put up a different QR code. This is the one that talks about, nope, this is the Washington Post. Nope, sorry. This is one that describes our Australia and how this rainbow image was made. So if you're interested in that.
Hello, my question is in regards, why can we see the auroras lower, closer to the equator, and if we have seen this before?
So the answer to that is yes, we have seen that before. In fact, when I mentioned that Carrington event from 1869, it was seen as far south as Colombia. So let me go back to this movie right here. The reason that you can see things further south is when a coronal mass ejection comes out from the sun, it's carrying a magnetic field with it. And if that magnetic field is strong and is oriented in just the right direction, it can start to cancel out the magnetic field of the Earth where they interact. And that allows the particles to stream in. The stronger the magnetic field and the more complicated it is, it can cancel out field deeper and deeper into the magnetic field. And as you can see, the lower latitude magnetic field lines are visible at lower latitudes as well. So the stronger the storm, the more it can essentially drill its way in, and that's why you can see it at lower and lower altitudes. The weakest ones would only be visible around the poles. Who's going to see 2026 eclipse? Who's going to see the 2045 eclipse? Everyone, I hope. Everyone. All right.
Well, I lived in Tucson for 4 years, so I think I can handle the Egypt one. So, all right. Well, thank you all for coming this evening. Let's give our presenter one more.
Thank you very much.
Looking ahead, we're hoping to have another presentation at the end of January to coincide with a meeting that's going on here. So just keep watching your emails.
If anybody has further questions, I'll be around until everybody's gone. Or until Andy kicks me out.
Nothing to do with the sun, but are you part of the Europa Clipper team?
I am not part of Europa
We
Clipper,
have
no.
a lot of you guys in the SWI. who
There
are
definitely a lot of my colleagues are, but not me. Yeah.
Aspects and Sudan. Well, thank you, sir. Appreciate you
My pleasure.
making the long trip from San Antonio.
Actually from Boulder.